So in section 3.4, we're going to learn the rational root theorem, amongst a few other things. And the rational root theorem feels a little bit antiquated because we've got so much sophisticated technology, but I also think that technology pushes us to know and understand the rational root theorem. And let me give you an example. Now, I gave you Desmos link to this function, and I've got it graphed here on Desmos. And the cool thing about Desmos, if I want to find the roots, hey, it's as easy as just point and click. There's one, there's another one, and here's the last one. All right, now a couple of these you could probably try and take a guess at, like negative 0.3333. You might go out on a limb and say that's negative 1/3. 0.4, okay. But how about this one, negative 0.4286? Well, that one's a little tougher, okay. So suppose all of these were kind of yucky numbers, and you're hoping that you had rational roots. Now, by rational roots, I mean roots that are nice fractions, one integer over another. Nothing like with a square root or pi or e or anything like that. Nice, simple numbers. Now, if you have a polynomial with integer coefficients and you're hoping to find rational roots, there's only a few candidates. Now, I've listed this one out for you because it gets kind of long, but basically you got to come up with two things. First of all, you have to find the factors of p. P is this last number here. And then the factors of q. Q is that first coefficient here. So here's all the different factors of p. Here's all the different factors of q. If this polynomial is going to have rational roots, and it's not guaranteed. You could have roots that deal with a square root. But if it has rational roots, they're going to be in the form of plus or minus p over q. So what you have to do is you have to run through and find all the different combinations of a value of p divided by a value of q. Now, this one is kind of long. That's okay. I did this one for you. The ones that I would choose to give you on an exam aren't going to be this long. All right? You've got 4 times 1, 2, 3, 4, 5, 6, 7, 8. That's 32 different combinations of all this stuff, not counting the plus or minus. So that's a lot. But if you had to do it yourself, you start out with a set member of the set of p and divide by q. So 1 over 1 is 1. 1 over 3, and then 1 over 5, 1 over 7, all the way up to 1 over 105, like this. And then you move to the next one, 2 over 1, 2 over 3, 2 over 5, and so on. Now, some of these, what you'll find, are going to give you, repeats. So, for instance, 3 over 15, that's the same as 1 over 5, so I don't need that one. And other places. 3 over 105, that's the same as 1 over 35. So again, I don't need some of these repeats. If you clean it all up, it looks like this. Now, let's take a look at where this graph actually crosses the x-axis and see if we can't guess a couple of these. So, in fact, I think we did guess a couple of these. One of them looked like it was at 1/3. And does anyone recognize the decimal value or as a fraction for 0.4? Well, it's 2/5. Good. Now, if you're unsure, you could type in 0.4 on Desmos and then click the answer to fraction button, and it says, oh yeah, 2/3. I got you. So, not bad. So we got two of those down. We need to figure out the third one. So that was 2/5. And we want to figure out the last one. So here's where our synthetic division stuff can help out. Let's go over to here. There's a couple ways we can do this one. Actually, there's a lot of ways we can do this one. But let's take our original polynomial, which was 105x cubed plus 38x squared minus 17x minus 6, if that's our p of x, then I know, for instance, p of 1/3 should be 0. So how do we do p of 1/3? Well, I just showed you how to use synthetic division in the last section to evaluate these things. So let's put the 1/3 out in front, and then 105, and then 38, and then negative 17, and negative 6. We'll put a little bar down there, add going down. And we'll start out our going down with what we always do, which is a big goose egg, right? So 105 and 0 gives me 105. 1/3 times 105. Oh, you know what? I almost made a terrible mistake. Our root wasn't 1/3. It was negative 1/3. Whew, I caught that just in time. Whew. So I'll put the negative in there, and the negative goes out in front. That makes a difference right here. 1/3 times, negative 1/3 times 105 gives me negative 35. Add going down gives me 3. What's that going to mean I'm going to put underneath the negative 17? What goes underneath there? -1. Excellent. -1. Add going down is negative 18. Multiply to go up. Well, that gives me positive 6. And bam. So nice. Nice. That means that p of x can be rewritten as 105x squared plus 3x minus 18 times x. What sign am I going to have to put in here to make negative 1/3 a root? A minus or a plus? Plus. Perfect. Now, if you want to help yourself out a little bit, we can do that. I'm not really keen on these fractions here. If you notice, each one of these is divisible by 3, right? So I'm going to factor out that 3. That's going to leave behind 35x squared plus x minus 6 like that. Boy, that 3 there is just begging to do something. And what it's begging to do is I'm going to distribute that 3 times the x and times the 1/3. So I'll get 35x squared plus x minus 6 times 3x plus 1. Beautiful. I factored out the 3. 3 is a common factor to all of these. 3 times 35 is 105. 3 times x, 3 times negative 6. So I just factored it out, and then I just distributed it here. Now you've got 2 choices. You can try your luck at factoring this, or you can use synthetic division with this reduced polynomial. And I know that there's I know one of the roots that go into this, right? Because I figured out 2 of them. I figured out one of them had to be negative 1/3, and the other one was 2/5. So I should be able to use 2/5 on this polynomial. Let's see. 2/5 into 35, 1, and negative 6. So let's see. We'll start out with a 0. As always, bring that down. 35. 2 times 35 is 70. 70 divided by 5 is 14. Add going down. 15. 2 times 15 is 30. Divided by 5 is 6. That gives me a 0. Beautiful. Beautiful. So what that's telling me is is that this can be rewritten as your constant, your coefficient of x, 35x plus 15 times x minus 2/5 times 3x plus 1. We can clean this up much the way we did just a moment ago. What number factors out of this? 5. 7x plus 5 times 5 times x minus 2/5. I think the next time I'm just going to jump right away and say, all right, factor out the 5 and multiply it by this. I'm not going to write this middle step here.
Is it 7x plus 3?
Yeah, thank you. 7x plus 3 times 5x minus 2 times 3x plus 1. And that's my polynomial. What's wonderful is that it's completely factored, and I can kind of see the roots on this thing now. But one of them, actually two of them we already got, right? Two of those roots were at x equal negative 1/3. So that's this one. X, come on. Negative 1/3, x equals 2/5. And can you do that one in your head? What would that be? If you set that equal to 0 and solved, 7x plus 3 equals 0, 7x equals negative 3. What does x equal?
Negative 3 over 7.
Thank you, negative 3 over 7. So x equals negative 3 over 7. Let's just take out a calculator real quick and get a decimal value for negative 3 over 7. So negative 3 divided by 7, 0.4286 maybe. Let's compare that to what we see on Desmos. Oh, perfect. All right. And if you're good with numbers, then you could just start out and say, you know what, I kind of think that that's negative 3/7. And you could check it with synthetic division. You could do a lot of different things here. But it's nice to know, what are the possibilities to start with. And that's where the rational root theorem comes in. So let's see here. The last one was negative 3 over 7. So that's this one right here. Let me put that in a different color. So ironically, they were all next to each other. So there's your three roots. They all happen to be, they have to be, if they're rational roots, then they have to be from that set. That's the rational root theorem. Now, is every problem going to be as long as that? Absolutely not. No. Sometimes you're just going to be asked to show me what are the possible rational roots, and that'd just be this right here. That's a good problem. Nothing wrong with that. In fact, I think that's the next one we're going to practice. Before we do that, any questions? All right. So, example B. That's all it is. It's just list the possible rational roots given by the rational zeros theorem. List your answers as a comma-separated list. All right. So, let's see. This is example B. Let me do that here. I'm just going to copy down the polynomial. Okay. So, switch over here. Oh, you know what? It'd help if I actually copied that down. P of x is 2x to the 5th.
Are we still on 3.4?
Yes. Plus 9x cubed plus 6x squared minus 6. Now, if you remember, there's two things we need. We need the p and the q. P is going to be a factor of this. Q is going to be a factor of this. So let's look at the possible values of p and q. So q, well, there's not too many things that factor into 2 evenly. So that's going to make this problem a lot nicer. It's just 1 and 2. Those are the only two possible factors of q. How about p? What are the factors of 6? 1, what else?
6, up to 3, and 6.
Thank you. 1, 2, 3, and 6. Now your possible rational roots have to be of the form plus or minus p over q. Now we're going to have to be a little bit careful here because they want you to list out all the answers. So plus or minus p over q, you just got to be methodical. We'll start out with the 1. 1 over 1 is 1, and then 1 over 2. And then the next one would be a 2, 2 over 1. And 2 over 2, do I have to list 2 over 2? 2 over 2 is already 1, right? So I've already got that one, so I'm just going to skip that one. And then 3 over 1, and what after that?
6. 6 over 1.
Let's do 3 over 2 next. I just want to be methodical, so I'm working on this one. I divide it by this and then this. And then I'll move to this one and divide it by this and then this. So the next one is 6. 6 over 1, right? And then 6 over 2. But 6 over 2 is 3. I don't need to list it again, so I'll skip that one. Now, if you were to input your answer, you'd have to input, let me put these kind of in order. 1/2, 1, 3/2, 2, 3, and 6. Those are the positive ones. You'd also need the negative ones. Negative 3 over 2, negative 2, negative 3, negative 6. So 1, 2, 3, 4, 5, 6, 12. You need to input all 12. That would be your answer, because I believe they're going to ask for a comma-separated list. But hopefully those are some gimme points if you're given one like this on an exam. Just list them, hey, no problem. Or maybe there is a problem. If there is a problem, let me know, and we'll fix it before we move on. Okay here? Back in the old days before we had cool things like decimals and graphing calculators, these would be the places that you would start. If you were trying to guess at a root, you'd start with one of these, and hopefully you got lucky, and then you could factor it down. Once you factored it the first time, if it's a cubic polynomial, then you have a quadratic that you can at the very least use a quadratic formula for. So it's nice to get 1 or 2 roots out of your system. That way you can deal with a smaller problem. Let's move on to the next one. All the real zeros of the given polynomial are integers. Find the zeros, including repetitions. Okay. Let's take a look here. So this is example C. Let me copy that down. Example C. P of x is x cubed plus 4x squared minus 19x plus 14. Well, since we have rational roots, in fact, they guaranteed that the roots are integers, it almost feels like it's not worth it to practice the rational root theorem. I mean, this would be your q, that would be your p. The nice thing here is that q is just 1. There's not a whole lot of things that go into p, right? 1, 2, 7, and 14. And if you looked at plus or minus p over q, that's going to be 1 over 1, 2 over 1, 7 over 1, or 14 over 1. And I'll just squeeze in the plus or minus out front, because it could be a plus 1 or a minus 1. Let's actually look at the graph of this polynomial. Do you want to do one on the graphing calculator just for good measure? Or, yeah, wouldn't hurt. I guess my big fear about using decimals all the time is that you might have with a structure that is not decimals friendly. That very well could happen. So let me clear this out. Let's enter in the function. So it's going to be x cubed. Make sure you press the right arrow to exit out of the exponent. Plus 4x squared minus 19x plus 14. Now here's something kind of cool that we got because we use the rational root theorem. And that is, I know kind of the max that I'm going to need for my window. Because if you think about this, this is saying that one of the roots has to either be negative 14, negative 7, negative 2, negative 1, 1, 2, 7, or 14. I'm going to take a bet that negative 14 or 14 aren't the roots. So if I want to set up my window, just kind of going on a limb here, I'm going to set it up, let's go from the negative 8 to 8 on the x-axis. And on the y-axis, it's like, oh boy, I don't know. I mean, 8 cubed is 512. If you don't want to mess with the y-axis, I am going to do one thing. I'm going to make y scale 100, like that. But if you don't want to try and figure out what values to use on the y-axis, press zoom and then 0. And I'll kind of show you what zoom 0 does. It's zoom fit. It's going to fit your graph on the y direction to the values of x that you gave it. So zoom fit is what you want. And bam. Yeah. Looks like I might have missed one. Maybe there was one at negative 14 or 14 after all, because I'm missing one. But I can see two of them. I can see I got a root at x equal 1 and a root at x equal 2. Darn it. I thought I was going to be so clever. Uh-oh. It changed things here on me, though. Let me go negative 7 to 7. It did something weird for me here. Did you guys do the same thing?
When I got it, I got
Oh, okay, yeah. Yeah, yours did something different there. I'm not sure what happened here. So I'm just going to go negative 500. Maybe I typed in the wrong thing instead of zoom 0. That should have worked. Then 125. Oops. 125. And graph. Okay. So yeah, we did get one at, it looks like negative 7. In fact, let's confirm it. If I hit the trace key and type in negative 7, look, it puts a point right on the x-axis, right? Negative 7 for x and 0 for y. So that's great confirmation. And in fact, let's kind of keep track of all our roots. We had roots at negative 7, 1, and 2, right? I can trace the other ones. 1 for x, another 0, 2 for x, a third 0. So every time I trace that, I'm getting exactly the same thing. Let's take a look at what that means for us. So I have roots at x equal negative 7, roots at x equal 1, roots at x equal 2. So those are our roots. Let's see the corresponding binomials. The corresponding binomial will be x plus 7. If I move this to the other side, x minus 1 and x minus 2. And that's telling me a couple things. But one of the things it's telling me is that p of x can be written as x plus 7 times x minus 1 times x minus 2. Beautiful. So I got the roots, I got how it's factored, I got everything. Nice. Of course, one goes with the other. If you've got the factorization, you get the roots. If you have the roots, you get the factorization. You should be able to go back and forth between each one. All right. Let's move down to example D, unless there's some questions on example C. Example D. So P of x is 3x cubed plus 5x squared minus 5x minus 7. So this right here. Again, we want to find some roots and factor this. It says, even if you need to use a quadratic formula. Let's go back to decimals for this one, because it just makes life so much easier. Wrong one. Here. So let me just cannibalize this one and type in the function. 3x cubed plus 5x squared. Now, if we get lucky and we can determine what the root is, then great. If not, we might have to take a moment, do the rational root theorem. I'll make that a small p, and there. There we go. So here, we got lucky. Right here, the graph crosses at x equal -1. Perfect. Now, we could have gotten that off the rational root theorem, but you know what? We didn't need to. So why make our life harder? But this is what we're going to do. We're going to start out with synthetic division. So it's going to be p of -1 should be 0. So let's test that. -1 into 3, 5, -5, and -7. What should that last number be when I finish my synthetic division? Anyone know? 0. Well done. Sharp crowd. Add going down. Of course, before we add, maybe we'll put in our favorite number. My hero 0. 3 and 0. -1 times 3 is -3. Add going down gives me a 2. -1 times 2 is -2. Add going down gives me -7. 7, and then bam, 0. So that's perfect. So this is x squared, that's your coefficient of x, that's your constant. That's allowing me to rewrite p of x. P of x is going to be something times something else. Can anyone fill in either of my somethings? One's a binomial, one's a trinomial.
3x squared plus 2x minus 7 times x plus 1.
Perfect. Since I've got a root at x equal -1, that corresponds to x plus 1 equals 0, just moving that to the other side. So that's this right here. Beautiful. Now if I'm trying to find where this crosses the x-axis, there's just a couple choices. It's where this is 0. We already know that. That's x equal -1. Or where 3x squared plus 2x minus 7 equals 0. And that one I don't know, nor do I suspect that it will factor. I would think that their instructions kind of reflect the fact that, okay, hint, hint, you're probably going to have to use the quadratic formula. So, A, B, and C. Let's see, 3, 2, and negative 7. Do you need a reminder on the quadratic formula? Don't answer that. I'll just put it up here because I'm sure somebody does. If you behave, I will not sing this to my favorite fight song. I've had students tell me that they've done that, seen that done. Although, the one that seems a little bit unbiased would be to sing it to Pop Goes the Weasel. So, I've heard that one as well.
Yeah, that's
Is that the one you've heard? Okay. Now, let's keep that off to the side here. Personally, when I fill this in, I like to start with a bunch of open parentheses. That makes a bigger difference if you have a lot of negative numbers, especially a negative b. 4 times a times c over 2 times a. And let's put some numbers in here. Negative of 2 squared minus 4 times a, which is 3, times c, which is negative 7, over 2 times 3. Well, that's going to be negative 2 plus or minus the square root of 4 plus 12 times 7 is going to be what, 84? 84 over 6, negative 2 plus or minus the square root of 88 over 6. I'm thinking that WebAssign will probably accept that, although honestly, let's see, 4 goes in there, 22 times, yeah. What you should get comfortable with is something like this. There's a perfect square that goes into that evenly. It's 4. So square root of 88 is the square root of 4 times the square root of 22. That gives me negative 2 plus or minus 2 square roots of 22 over 6. Coming down over here, I'm just going to recopy that. The tempting thing that I see people want to do all the time is you cancel, oh, I'll cancel that 2 into the 6. You can't. All right. If it's killing you that, gee, there's something here I can cancel, here's what you can do. Let's factor out a 2 from the numerator. So I'm going to factor out big, juicy 2. What's that going to leave behind? Well, negative 2 divided by 2 is negative 1, plus or minus square root of 22. Now that I've factored it, now that there's multiplication between these terms, now I can cancel and get negative 1 plus or minus the square root of 22 over 3. You should be able to do it that way. An alternative to that, which gives you the same thing, is if you split it up as negative 2 over 6 plus or minus 2 square roots of 22 over 6. And that gives you negative 1/3 plus or minus the square root of 22 over 3, which is the same thing as this. You've got common denominators, you can bring it together. I like the first one. I can't stop you from doing the second one. So whatever works for you. Overall, we have 3 roots. We have x equal negative 1, x equal negative 1/3, plus the square root of 22 over 3, and x equal negative 1/3 minus the square root of 22 over 3. In WebAssign, you'll probably have to list these. For me, you can give me x equal negative 1 and x is plus or minus this. I'm fine with the plus or minus. WebAssign, you're going to have to list them out, sorry. Do some copy, cut, and paste. You probably save yourself some keystrokes. All right. Hey, wait. Let me photobomb. All right. Let's keep going. How are we doing at home? Doing okay there? You know, might be piping into my headset here. So let me see. Can I hear from my homies? Doing okay? Earphone, speakers, headphones. Let's try it again. Someone say something. Still not getting anything. All right. Let's keep going. You can put things in the chat if you have some questions, and I'll try and catch it there. I'm hoping we're getting pretty good at these things. Let's see. Let's do this one, except this last one, we're going to be a little bit clever about this one. All right. We're going to look at the graph and kind of decide a few things based on the graph. All right. Now we will practice synthetic division once, but overall, let's move on to example F. We've got P of x equals x to the fifth minus x to the fourth minus 5x cubed plus x squared plus 8x plus 4. Okay, let me graph that. Oops, darn it. I hate that. We'll shut this one off. And it was x to the fifth minus x to the fourth. Wait a minute. There we go. X to the fifth minus x to the fourth minus 5x cubed plus x squared plus 8x plus 4. All right. So what on earth does that thing look like? Let me zoom out a little bit. This way. Okay. That looks kind of good. Now we can see the two roots here, right? We've got a root at -1 and we got a root at 2. So if I wanted to, and I'm only going to play this game one time, if I wanted to, I could get at this by synthetic division, because I know that p equal -1 should be 0. And let's test it. I'll put a -1 out front here, and that's going to be 1, -1, -5, 1, 8, and 4. Add going down, 1, -1, -2, 2, -3, +3, 4, -4, +4, -4, and 0. Excellent. So that's telling me that p of x can be rewritten. It's now x plus 1 times x to the fourth minus 2x squared, or 2x cubed minus 3x squared plus 4x plus 4. And I could do the same thing again with -1. But I don't need to. I'm going to get this all in one go. Let's do this the easy way. So let's take out our root. And then, let's see, the binomial and the multiplicity. So I hope you've been watching some of my earlier videos, because we're going to go back to our bounce and wiggle lab kind of stuff. So we'll look at those. And I had roots at x equal -1, and one more. Was it -2, or is it 2? I'll give you a second to copy that down, and we'll look back. So we want to look at our roots, the corresponding binomials, and the multiplicity. I probably could have looked at the behavior and then switched that to multiplicity, but we'll take care of it nonetheless. Let's look back here. We had roots at -2, -1, and 2. So those are our roots. What are the corresponding binomials? If x equals -1 is a root, what's the corresponding binomial? It would be x plus 1. And this would be x minus 2. Let's look at the behavior of the binomial at those roots. So let's come back here. And let's start out with the -1. Now remember, your choices are bounce, wiggle, and straight through. So what are we going to get here? Is that a bounce, wiggle, or straight through?
So wiggle.
That's a wiggle. All right. So that's a wiggle. And how about somebody for this next one? What are we getting over there at 2? What kind of behavior? Is that a bounce, wiggle, or straight through?
Bounce.
Bounce? Do we agree on that? Well, it doesn't cross the x-axis. It just touches it, kind of kisses it, and then bounces back. It's going the other direction. It doesn't cross through, like, say, the graph of y equals x minus 6. Let's see, let me do -1. That one just buzzes straight through. It doesn't stop. This one has a little bounce in it. Now, to remind you of those behaviors, when you had a bounce, that was an even exponent. So let's make that the first even exponent we can, which is a 2. And a wiggle had to have an odd exponent greater than 1. So the first one we can come up with is a 3. So we have multiplicity 2 and multiplicity 3. That gives us our degree 5 polynomial. In fact, what it's telling us is that this would eventually factor into x plus 1 to the 3rd power times x minus 2 squared. That is, if you did synthetic division 4 more times, you know, insert finger in throat and gag, that's eventually what you would get. All right? But I think this is a much cleaner approach. Just saying, you know what, hey, I know the behavior of the polynomial near those points. We'll reverse engineer it. Beautiful. Done. And we also reviewed synthetic division along the way. Cool. All right. Looking okay on that one. Now, it's going to ask you to list these numbers. And this is important. When you're doing the homework, it's going to ask you to list these numbers separated by commas. So you have to list the repeats. Even though it's multiplicity 3, they want you to list -1, -1, -1, and then 2 and 2. So kind of a drag, but yeah, it is what it is. Let's see if we can do this one. I gotta admit that I'm pretty keen on something like this for a test question. And maybe we'll do a couple of these. And we're going to go kind of back to our days with bounce and wiggle labs. So it says graph below is a polynomial. Let's figure out the function that it represents. So we'll start by noticing the roots. So this is example G. Roots, binomial, behavior, and multiplicity. Yeah, ran out of room. So in case you're curious what I'm writing down, it's this. Roots, binomial, behavior, and multiplicity. Let's look at the two roots. Gotta get rid of this icon. Back over here. The two roots are at -2 and 1. So let's write those both down. X equals -2, x equals 1. The corresponding binomials, pause the video and test yourself if you like. X plus 2 and x minus 1. These binomials correspond to a polynomial with those roots. Let's figure out the behavior of the function near these roots. Start at -2. What kind of behavior do we have at -2?
Bounce.
It bounces. So we get a bounce. And then over here, that's not a bounce because it goes from one side to the other. Didn't stop.
Wiggle.
That one's a wiggle. Wiggle. All right, so we got that. Now the smallest number that creates a bounce in terms of a multiplicity would be a 2. What's the smallest number that would create a wiggle?
3.
3. So that gives us a degree 5 polynomial. That's looking okay. So P of x would equal x plus 2 squared times x minus 1 cubed. If you graph that, you'd be disappointed. It wouldn't quite fit. It'd be off by a little bit. Let me remind you about something. Maybe, let's see, do I have that handout here still? Is it 3.2? Yeah. No, not there. Yeah, here we go. Remember there were several different behaviors. So if your polynomial goes down in one direction and up in the other direction, then it has to have an odd degree, right? So clearly we got something of an odd degree with this one. And let's see, I got to jump back to here. That's clearly an odd degree, but there's something else missing with our odd degree here. What is it? What's going on there? Does ours start from the bottom left and go to the upper right like this one? No, it goes from the upper left down to the bottom right, which means it has a negative leading coefficient. It has to have a negative to start out here. So if you want to keep it simple, we'll just put in a negative like that. You can put in a negative with any number, it doesn't really matter, because it's still going to have the same roots and it's still going to have that kind of behavior. It just could stretch or shrink it one way or another a little bit. Nice. Doing good on that one? Let me go back here. Do you want to try another one? Let's try one last one. I'm going to write the same kind of things here. Example H. As I'm going to write a column for the roots, and the binomial, behavior, and then the multiplicity. So we got roots at -1 and 2. And then the rest is kind of up to you. Decide what binomials correspond to them, what's their behavior, and then the multiplicity. And you should be able to get almost all the way there. So the binomials that correspond to this would be x plus 1 and x minus 2. What behavior did we have at the root for x equal -1? What kind of behavior was that? Was it a bounce, wiggle, or straight through? Straight through, right? Isatu, you've seen that this one is going straight through as opposed to this one over here.
So are we looking at it, like going down to up? I thought it was balanced.
We are going to take account of the fact that both of these are pointed down. Yeah, we are going to worry about that in a minute. But right now, are you comfortable with the distinction between straight through, which is at -1,
Yes,
and then wiggle?
Yeah, I guess I have to review that.
Okay. All right. So, but hopefully you can see these by contrast. Straight through just goes right through without pausing. Here it kind of says, well, I'm going to flirt with negative or +2 for a bit and then go through. So it doesn't just zip right across the x-axis. So the behavior is straight through, and this one is a wiggle. Now the smallest multiplicity that gives us a wiggle is a 3. And straight through only happens with multiplicity of 1. So that tells me I have a degree 4 polynomial, which makes sense given the fact that both of these point down. I mean, that's something you can see with a degree 4 polynomial, and you see it right here. When you have even degree, both of the tails or the end behavior go in the same direction. It's just one last thing. What else do I have to take account of to get this problem completely right?
Negative coefficient.
Yeah, I gotta have a negative leading coefficient because both of these point down. So I'll just put in a negative right here, and then I'll be good to go. So it's gonna be p of x equals negative of x plus 1 to the first power times x minus 2 cubed. And man, you got 6 out of 6 points on that one. Good for you. Okay, that should do it for this section. So good luck with this stuff. Review this if you need to. There's going to be a test next week.